Hello, welcome to recap lecture number 5. In this lecture, we're going to be largely focusing on the fundamental theorem of calculus. Understand that in our class, we refer to the fundamental theorem of calculus part 1 and part 2, and that is true in most textbooks. However, sometimes the labeling is exactly the reverse of what we experience in our class. So for that reason, when you're writing your anything, when you're writing anything, a justification, a reason, anything on your AP test, please don't refer to part 1 or part 2 because that's not universal. However, just call things that are referring to the fundamental theorem of calculus, just call it by that. I think that the abbreviation would also be fine. But just don't label part 1 versus part 2 necessarily. You could say fundamental theorem of calculus and then write the part that you are referencing if you would like. So what we have typically called part 1 is this statement here, which is to explain that the area under a curve can be thought of as an antiderivative evaluated at the two bounds and then finding the difference between those two. And then what we have called in our class the fundamental theorem of calculus part 2 has to do with taking the derivative of a function that's defined by an integral. And one of the bounds typically has the independent variable in it. And so you might not see these as being especially related, but they are. If we take a look at this statement, for instance, we could say, well, that statement on the left is the same as saying find the derivative of, and then instead of writing the integral part, this part here, we could use the first part of the fundamental theorem of calculus, what we call the first part, and say, well, that's just finding the antiderivative, which we'll label as a capital F, and then evaluate it at the two bounds. And if you do that, then taking the derivative of this should make some sense, because if we take the derivative of capital F, we're going to get lowercase f. And if we take the derivative of this guy over here, we should understand that capital F of A is going to be a constant, which means that its derivative is 0. So that's just regular f of x. And now if you take a look back in the box, that's exactly what that says. Okay, so it comes from what we call in our class the first part of the fundamental theorem of calculus, and that is why, indeed, I've always taught that part first, because I can see where this second part comes from if you take that other part first. And then the second statement down here is just a more generalized statement. Instead of having the top bound be x, it's just any function of x. And if we were to do the same sort of explanation that we did up above, we can say, all right, this left-hand side of the equation here is just the derivative of, and then lowercase f, we can denote its antiderivative as capital F, and then plug in the bounds by fundamental theorem. And then we're going to take the derivative, because that's what this symbol out here means. So take the derivative of capital F means get lowercase f. And then we're going to keep the inside part, and then take the derivative of the inside because of chain rule. Okay, we're taking the derivative of a composition of functions. Okay, so you take the derivative of the outside, keep the inside times the derivative of the inside, and then the derivative of this part would again be 0. So you could write minus 0 there, or understand that it is 0. And this statement that I just wrote is what you see right here, up here. Okay, so those statements I hope make very good sense to you, and hopefully if you ever get confused, you can do the sort of writing that I did, right here and here, to sort of straighten yourself out. Okay. One thing that is tested quite frequently is the idea of a accumulation function, or what I think I called in class back in the day, a slider function. Okay, so I just magically made a little picture for us, and in this picture, the function that you have drawn here, this little squiggly line thing, let's understand that to be f. And then the idea, or the definition that's up here, is the idea of a slider function. So this guy here is saying that the function g is the accumulation of area under graph f, starting at A, so to speak, and going until any value x. And notice that x is that independent variable in this statement. So the way I describe this in class is let A be the green line here, and then X is a variable, so it can vary, it can change, and X can take on all these different values as we move this purple line across. And so if you imagine that as I'm sweeping this across, imagine that that shape was also coloring in this space. And so as that slider goes across, as X changes values, there's more area that's accumulating behind that. And we can even think of that slider going to the left of A because we understand how to switch the bounds on an integral, etc. So the idea here is this accumulation function, and you're going to see that a lot in the examples that we have coming up, and it's a very commonly tested idea. All right, so here we have an AP style question. It is not actually from an old AP. This is written by a retired math teacher, and he wrote out this question, and it's calculator active. Notice, please, that when things are, especially free response questions, when free response questions in particular, calculator active, means you are supposed to use your calculator more often than it means the calculator is just nice to have. It mostly means please use your calculator. That being said, please never ever write in your free response questions calculator lingo like that. That does make the professors who grade AP tests kind of cranky. So we do want to try to write correct mathematical notation. So like an integral sign with your bounds, etc. Right, write the right thing, and then use FNInt, but don't reference it by name in particular, okay? Because that is not universal. Mathematics is universal. TI calculator lingo is only universal to people who have a TI calculator. Anyway, enough said. This one says a company is offering a coupon for money off at a popular chain restaurant if people respond to an online survey. And then this is something I've seen several times, and I don't love it, but I understand that they're just trying to make sure you really understand things. They say the rate at which people answer the surveys is given by this particular function that they're referencing. I'm trying to make this go away. Little box. Anyway, there we go. So they're saying that A of T is the rate at which people answer surveys, but notice that it already is a rate. So think of that function the way you would think of some derivative function, even though it doesn't have a little prime in it. And they did the same thing here. The rate at which the coupons are mailed out to the people who answer the survey is given by function M of T. So we have two functions here that already are describing rates. And they say both A and M are measured in people per day, and T is measured in days. And the domain of T, or the domain of the functions, are from 0 to 30 for the month of June. And they say at the beginning of this whole deal, 100 surveys have already been taken, but they haven't sent out any coupons yet. So they start out with this initial condition right in here. And we do need to pay good attention to that. It is very common for that kind of information to be in the stem of the question, but maybe not be used until later in the question. So we just need to make sure we don't forget that. Okay, there are a lot of parts to this question. And so what I'd like us to do is just pause the video, give it a try, and then come back and we'll check your work. Okay, I hope you've taken the time to try this yourself. You certainly will learn more by trying before you peek. All right, so part A asks how many people answered surveys by June 15th. So this is where we are going, one of the places we need to use our initial condition of 100. That's how many surveys were in the bank as of the beginning of June. And then there are more that are accumulated through the month of June, but we were just asked for up to the 15th of June. So we use the bound of 15 to signify that, and you can see my work there. Notice just in terms of writing for your AP test, if you have some ugly function and it has a name like A of T, use A of T. Do not feel that you have to write out what the equation is. If it's defined in the stem of the question, you can use its name, A of T, for example. And then you can just go ahead and throw that on your calculator. I did not write, I was using FNInt or anything like that. I just found my answer. They know you have a calculator because it's a calculator active section. They'll understand how you got that answer. In part B, they said they're going to send up differing amounts of coupons. And so this was the $10 coupon. This is the $5 coupon. And so I'm taking the value of the coupon times the number of coupons of that type. So this is the part I just underlined is the part from part A, the quantity from part A. And then we're taking the $5 amount, and then this would be the number of surveys to whom this would apply for the second half of the month. And so it's going to be $10 coupons for that many and $5 coupons for that many, and that would be the total value. In part C, you can see that we have to bear in mind that we already are looking at a rate. So we are finding f of 15 here, and so we are just putting in 15. We start with our initial amount. Our initial amount was 100 because this was not anything, and then we add on the difference between the two, the ones that are coming in and the ones that are going out. And so there are 420 people who answered the survey, but their coupons have yet to be sent out. And then part D, you're asked to find f prime of 15. So you can see that what I did was I first wrote here something that was just in general. Then I plugged in the two values. I plugged in 15 into the two parts. I found that to be a negative amount. And this indicates that what we're doing is we're closing the gap. We started with, started the month with this backlog of, oh, here's all these surveys that have been sent and we haven't even started sending out the coupons. As time goes, we're kind of closing up and closing that gap. And so the difference between the two is negative, which means that the rate is a decreasing rate. So people who did the survey but coupons not set yet is a decreasing rate at this amount as of mid-month. Okay, we're getting caught up. All right, question B is question B2 is a funny one about Jack and the beanstalk. And again, this is calculator active. So Jack is climbing down a vertical beanstalk that goes down to the ground, and the giant is chasing him at time equals 0. So at the beginning of our story, so to speak, Jack is 1,600 feet up off the ground, but the giant is just behind him at 1,000 feet off the ground. Both only have enough strength to climb for 60 minutes. So at the end of an hour, that's the end of the whole, chasing down the beanstalk fiasco. So Jack is moving at a certain rate. This is similar to the previous question in that you're given a function that is itself a rate. Same thing for the giant. You're told the giant's rate of motion. So you're asked again to do several different parts of this question. Just like with the previous one, I'd like you to pause and then come back to check your work. Okay, we're back to talk about Jack and the Beanstalk. In the first one, you're asked how far does Jack climb in 15 minutes? So you're really just looking for his distance traveled. You're going to take his rate and integrate it from 0 to 15. And you can see my answer there, the 690-ish number. And then in part B, you're asked what the distance between Jack and the giant is at time equals 15, and is it increasing or decreasing? So for this, you need to include the initial condition for each of these guys. This is Jack's initial height. This is the giant's initial height. They're both going down the beanstalk. So I subtracted how much they've traveled. And this is the location of Jack at time equals 15. This is the location of the giant. And then if we want to know if something is increasing or decreasing, we want to look at, is the derivative positive or negative? Well, since these both are already rates, you can think of them as being derivatives. Even though they don't have a prime, they are rates, and derivatives are rates. So we're looking at, is this derivative positive or negative? And it is positive at time equals 15. So therefore, at time equals 15, the distance between them has to be increasing. In part C, in a similar sort of way to what I was just talking about, we are looking at finding a maximum, and we look for critical numbers by setting the derivative equal to 0. So that was what my first line of writing here says, letting the derivative equal 0, which is equivalent to letting the Jack function and the giant function be equal to each other. I solved that through looking at my calculator and finding that time equals 29.7-ish is where that happens. And so then I did interval testing, and then I wrote a nice sentence. So remember that your AP graders, although they very well are going to understand what you mean by a thing like that, are specifically instructed not to look at it, because that sign chart could mean something about G, it could mean something about J, it could mean something about G prime, J prime, who knows? There's so much ambiguity that's possible, that the clearest thing that the AP graders, council have kind of come up with is we're just not looking at sign charts, and the burden is on the student to write a sentence or more than one sentence. So this is the kind of sentence, because the rate of change is positive on this interval and the rate of change is negative on this interval. That means we have to have a maximum at this particular critical number, okay? And part B was just to write something along these lines, just basically trying to figure out when is it that Jack is going to reach the bottom. And he was 1,600 feet off the ground to start with, and this would be the time at which that happened. And it said we didn't have to solve it, so yay us. And I wrote a little note there about how the giant stairs, just so you know, in case you're getting caught up in the drama. Okay, there's one more question I'd like us to take a look at, and then you are done for today. In this example, there isn't a story, and it is not calculator active. So these are all, I'm just going to have us do part A, but all of these things are things that you should be able to do on a graph like this. And something to note is what you're looking at a graph of. This says we're looking at a graph of F, and understand where F is in this. So this is that slider function idea that I was referencing. Notice that in the first part, the part that I'm asking us to do, we have to find three different things. We need to find G of 2, G prime of 2, and G double prime of 2. Okay, pause the video, come back and check in just a bit. Okay, so one of the things that I like about this kind of problem is that you do need to think of each of these three little question bits as sort of different things. They are different kinds of entities. And the first one, G of 2, you're just putting a 2 in for x. And so if you put a 2 in for x right here, you got to put a 2 in for x up there. And so 2 becomes the upper bound of your integral. And that just means you're finding the area of these two little triangles. And so that's what I've shown here in my work. So the thing that I like about this part is that you have to think about area. In the second part, you need to think about the fact that when you take the derivative of this function, ooh, that's wild. That's not what I was trying to do at all. So when you take the derivative of this function up here that's defined by an integral, you're actually using that fundamental theorem of calculus that we referred to earlier. And so what I wrote down beneath here, if we can get it to scroll, very good, is this. So G prime of x is equal to f of x. And so if you plug in 2's for both of those, you get this statement. So in trying to find G prime of 2, I'm actually just looking for f of 2. And lo and behold, we have a graph of f. So f of 2 just means I want to look at this point. Having all sorts of drama here. Look at this point right here and figure out what its function value is, which is a 1. So the second part of this question is literally just finding a point. An ordered pair. And then the third part of this question is yet a different way to think about things, because G double prime means that I am finding F single prime. So G double prime would be F prime. You can just get that right here from taking the derivative of the line up above it. So G double prime is the same as finding F prime at a particular value. And so this is like finding slope. So we want to go back to our graph and find its slope, and I say it's 2 over 4 or a half, because right in here we have a rise of 2 for a run of 4, and that's good. Okay, so 1/2 should be our last answer. Of course, there are other parts to that question. If you care to do them, I would be happy to look at your work and make sure that you are on the right path. I will see you in class. Thanks.